because if not, your waters are going to look weird. So, water interacting with water. Here's one water molecule. Those lone pairs, right? These lone pairs are super, super negative. These H's, fairly positive, right? So if I orient another water molecule with this, what of the second molecule, what's going to be oriented or attracted to the hydrogen down here? The oxygen of the other one, right? So if I draw this correctly, I'm going to draw this like here, H and H. So here's two water molecules. The hydrogen bond is literally a simple attraction. There's no touching, there's no H between the two of them. It's just an attraction between this part, the positive part of this molecule, and the negative part of this molecule. It's like this invisible beam of attraction. That's it. So there's nothing funny between the two. It's just a simple attraction, okay? So that's what a hydrogen bond is. This attraction is strong, though. So this is stronger than most other intermolecular forces. So that's why it causes like the different properties like high melting point and stuff like that. Surface tension. It also makes other particles attract that way, so water can it's polar, so it can dissolve other polar things. So this is a quick review from yesterday. Okay, so these right here. What's your favorite one? 1, 2, or 3? We'll do one of these right now. This is a review from Percent Comp. 2. Okay. How much iron can be recovered from 25 grams of? Name that for me. Name it. Iron. Iron what? Iron 3 oxide. So no, you said iron 2 at first, but it's iron 3 because this is technically iron, and that 3 came from up top. This 2 came from oxygen, so you call it by its charge. So iron 3 oxide. So iron 3 oxide is going to have some iron in it, right? How much iron? I don't know. So for us, what we did yesterday was we said, okay, we have our total grammage here, and we have our identity of our chemical formula. We can actually get the percent of that thing and just multiply by the total mass, and we can get whatever grams are present of the iron. So we need to figure out percent what to solve this problem. Sorry, I just told you, percent iron. So how do I figure out percent iron from this? Anybody? Alex, what you got? How do you get percent iron from this compound right here? You guys have your notes from yesterday. How do you find percent of anything? Darian?
You add up the mass and then see how much.
Okay, so let's add up the total mass first, right? So periodic table out. And so I'm forcing you guys to answer these questions because based on your feedback from yesterday, I typed up your successful tips and your things that you would change if you were trying to become more successful. Why does the Word document not want to work for me? Okay, so it's really little. Let's see if this will come up. It's being super weird. My lovely computer. Okay. I'll show you that in a second. Let me see if I can. Well, I'm going to read this off to you. So, success comes from, this is just from what you guys said in my second period said. So I just kind of combined the list. Taking good notes, not only what is written, but what is said. Okay, completing every example in class with Ms. E, so that you guys have something to look back on. Answering questions in class, asking questions in class. Reading chapters with the reading guide instead of just searching for the answers like online or doing the reading guide just by searching for the answers through the book. So I'm trying to start implementing these and asking you guys to do these things with me because if it's helping some people be successful, maybe it'll help you. So what's it going to hurt? We're going to try to do this together here, okay? So Darian said find the total mass. So iron, so there's 2 irons and right here, and there's 3 oxygens. What do they weigh? Iron weighs what? 55.85 plus 3 oxygens, which each weigh 16. Okay, calculator, who's got that for me? 159.7. Okay, is that what you said? Okay, so that's our total mass. Now, how do we find percent iron from our total mass?
You divide by 2.
2 times the 55.85, right. So this is the total, so this is going to be in the denominator. Iron is going to be whatever iron's worth, right? So there's 2 irons, each weighing 55.85. So 2 times 55.85, is 111.7 grams of iron. So we have grams of iron from the sample over the total grams times 100, and that's going to give us percent iron. It's just part over whole. So the part that we're looking for over the total sample. So that divided by 159.7 is 69.94%. All right, so now we've got the percentage of iron, but we still don't have the answer. Josh, what do you do to find the answer for number 2? Right, so we're taking our sample mass, the 25 grams, and we're multiplying it by the percent iron to figure out of the 25 grams how much of that's actually iron. So it's just simply, it's a math problem. Chemistry is just fun math. I would tell that to any math teacher. So get on my level. Okay. We have to change our percentage to decimal form, right? Because you know that you can't have over 25 grams of the substance being iron because there's not even 25 grams to work with. I mean, there's only 25 grams to work with. So 25 times your percentage to give you 17.49 grams of iron. So then if I asked you one last question for this, if I said how much oxygen is present, what's the easiest way to do that? Yeah, your sample total is 25 grams minus your sample of iron, so that it should be like, what, 7.51 grams? Yeah, 7.51 grams of oxygen, because that's kind of the rest of the 25 gram sample we have. Thumbs up, you're good with this. All right, so I'm trying to do a little bit of question regarding each of the problem sets 10 questions today. All right, so I'll go back and do the other ones if you want me to later. So empirical formulas is our last topic for this first half of the unit. So basically, we've gone over conversions with the mole. We'll be reviewing those today. We've gone over percent comp. We just kind of reviewed that just now. We're going over empirical formulas and molecular formulas. And tomorrow we have an activity with that. So today I'm going to teach you. We'll do some practice in class together and make sure we're all good. Prop set 10 is due tomorrow. I'll let you write down a little bit before I start talking. So let me take good notes for Jess and Ashley. Just figure out who sits where. Abby. There's Abby. Maybe it's the luck of the Irish here. Okay, so I'm going to go through, I'm going to let you guys write just a little bit more, and then I'll go through some of these. And some of you guys still haven't taken the Socrative quiz, and I will open it back up. I have to close it daily to make sure that I get the grades from people who have taken it. So that's that bonding one we had like last week. So if you've not taken it, since you're in the watch for it, I want to make sure that you get that sort of thing care.
Is that the one that had only a few questions on it?
Yeah, it's like 9 questions. Okay, so I'm going to scroll back to the bottom just a minute, but let me go ahead and start up here. So we've got empirical and molecular. Empirical formulas are always just simple formulas. We've reduced all chemicals, all ratios down to the simplest ratio possible. I mentioned that a lot when we talked about reducing all ionic formulas. That's just exactly what I'm talking about now. We're just going to actually start calculating them from data versus like, oh, hey, my formula is Fe2S2, you know, where you go, oh, I need to reduce that down to FeS. So we're actually going to go through some data with that and calculate it ourselves versus being given a formula. The molecular formula is just going to be a more complex version of the empirical. They're in a complete they're a product of one another. So the molecular formula we're going to talk about in just a minute, but they're just an expanded version of the empirical formula. So empirical is just the smallest whole number ratio, simplest ratio. So for hydrogen peroxide here, I technically can reduce that down to what? What? H1O1, right? But we don't write that, right? We write this. So I can kind of reduce it down to something like hydroxide. It's just me reducing from a ratio that's the same. I can divide by something and reduce it down to the lowest possible ratio. So for glucose, C6H12O6, what can I reduce that down to? CH. What am I dividing each of these by? 6. Okay, so 6 divided by 6 is 1. 12 divided by 6 is 2. O divided by 6 is 1, right? So I can reduce that down to CH2O. And this is what you actually learn in biology, that all carbohydrates are 1 to 2 to 1 ratio, right? It's just any carbohydrate past the 1 to 2 to 1 ratio called, it's just a polysaccharide because there's more than one carbon. And also it's a molecular formula for something like that, okay? So anytime we wrote an ionic formula, we naturally always reduced it. So you're already very familiar with the ionic formulas. That's what my example was earlier when I was going, oh, Fe2S2. What's the name of this one? What is it? Iron what? Right, iron 2 sulfide, but we don't write iron 2 sulfide like that. We write iron 2 sulfide like this, because you always reduce. So we've done that, for the past couple or two, I guess, week or so, just like we've always done with anything ionic, okay? So molecular ones are going to be they're called the true formulas. They're literally what exists in the molecular form. No reducing needed. If I want to know the true number of carbons and the true number of hydrogens and the true number of oxygens, I don't reduce. So in my previous example up here, my true formula for glucose, it's not C1H2O1. That's not what glucose is. Literally, glucose is C6H12O6. I'm essentially telling you it's the unreduced version of whatever you were talking about. So those are the two things we're going to learn how to do today. And we're going to do those from percent composition, which actually is a good, easy way to do it. I'll have just and so for this whole number ratio that I'm talking about here, it's basically my empirical formula. So for my empirical formula for this carbohydrate, previously I just did C1H2O1. So what am I going to multiply all of these by on the outside to get C6H12O6? 6. So the whole number ratio that I'm multiplying by is just 6. So that 6 distributes in to make C6H12O6. So that's what I'm talking about, just a whole number ratio or a multiple of that. I'll give you guys another second there. Everything else is like problem solving after this. This is kind of just the introduction side. Okay. I'm just passing out random papers. I'll come back here if I need to. Okay, so look at these with me. You don't have to write much down unless you want to. For these, label these as empirical or molecular formulas based on what they look like, okay? So C4H02, empirical or molecular? What do you guys think? Can you reduce these subscripts down further?
Yes.
Which ones?
1.
But what would you divide the 1 by? Can you divide them all by 2? No, you can't divide 1 by 2. It's going to give you half. And who puts a half subscript there, right? So this is actually empirical because we cannot reduce it any further. That's an empirical formula for whatever that thing is. Okay? This one, C22H44O11. Can you reduce all those? Yes, by what? Or what are you dividing by? 11. So you divide this by 11. So it would be C2H4O1, right? So the way it's written here is a molecular formula. What we've just done is we've reduced it to the empirical formula. Next one. Empirical or molecular? Empirical, because there's no way you can reduce the 1 any further. It's at the slowest possible subscript. So that's an empirical formula. The next one, empirical. You automatically should recognize that as empirical because it's ionic. We always write all ionics in their simplest form. Previously, though, what was the number here and here before we reduced? 2, because calcium is a 2, sulfate is a 2, crisscross, you get C2, parentheses, sulfate 2, but we reduce them down to 1 and 1 because that's how empiricals always work. And then the last one, I'm going to say molecular here because it technically can be reduced, but mercuries are weird. Mercury's form this like dimer thing. It's actually this is actually the empirical for us, but I'm going molecular because there's sometimes exceptions here. All right, so if you want to write down one of those examples, go for it. But it's pretty easy to recognize if you can reduce, and you're not too empirical yet, so you got to get to the point where you can't reduce any further. Okay. All right, so before we learn how to solve, I like to give you a step-by-step process on how to solve some problems because that way you can always refer back to the point where you don't have to look at your notes anymore, okay? So if I give you a step-by-step process on how to calculate molecular formulas and empirical formulas, you'll never be able to fail at this, okay? Follow your step-by-step process. So I'm going to let you guys write down the first 3 steps. After that, it talks about rounding. I'll talk about the rounding as we go through some examples. So every time you're going to write empirical formula, just put EF. It's a little shorter. Okay, so first step was you had to convert everything to moles. Let's say I give you grams of carbon. How would you get from grams of carbon to moles of carbon? What's that conversion factor? Think. Huh? If you've been doing problem set 10, this should be like the back of your hand. You should know it by heart. How do you get from grams of carbon to moles of carbon? Grams per mole, right? It's molar mass. That's the conversion. It's molar mass. That's what we call it, okay? Be confident in yourselves if you want to answer, okay? So if I have grams, let's say I have a specific number of grams of carbon. So get 2 moles of carbon, I put 1 mole of carbon over what's the molar mass of carbon? Here are our tables. Huh? 12.01 grams of carbon, okay? It's no secret what it is. You just have to be able to find it on your tools. So if you have your grams, you can get to moles by doing that. Then you'll end up with moles of carbon, moles of oxygen, whatever you want to convert to, you can do that because grams and grams cancel. Okay. Once you get moles of everything, you choose, maybe you have 3 different things you're looking at. You choose the lowest number of moles and divide them all by that lowest number of moles. Basically, get you a ratio. That's all subscripts are. You're like a 1 to 2 to 1 ratio. It's just to the lowest possible ratio that you need, okay? So you have to divide them all by the moles. That's the smallest number of moles that you just calculated, number 1. After that, those numbers, if they're whole numbers, those are the subscripts. So if you got number 2 and they're all whole numbers, like 1, 2, 3, 4, something like that, those are the subscripts of the formula. If they're not exactly a full integer, then you have to round them. How do you know if it's roundable? There are some rules to rounding, okay? So if it's roundable, like being a 0.2 or lower, so like if it's like 1.2, round that down to 1. If it's 0.8 and higher, let's say it's 1.8, round that up to 2. Those are roundable numbers. But then you got that wiggle room in the middle. You're like, well, what do I do? If you cannot round to up or down, then you have to multiply by some other integer to get to a whole number. So let's if there's like a 1.5. 1.5, you're not going to round up or down. Okay? You're going to multiply it by 2 to get to the next whole integer. So if you had a 1.5 as your division thing that you just did number part 2 up here, you multiply that by 2 to get 3 as your subscript. If you had a 0.3 ending, you can't round that up or down. You have to multiply by 3. So if you did 0.3 times 3, that's going to get you to, let's say it was 1.3, okay? It was 1.3, multiply that by 3, what do you get? 1.3 times 3. 3.9, right? So 3.9 is still not a whole number, but guess what? It's really close. I would round that up to 4. So once you multiply, you can round from there, but your whole business of multiplying is just to get really close to a full integer, so you can call that your subscript. So these are just the rules of the trade here. So these are hints, because sometimes you're going to work through it in your head going, oh, I don't know, what do I do with 0.66? I can't round it up, can't round it down. If I multiply by 2, that only gets me like 0.32, 0.32, you can't round up or down, so you multiply by 3 instead of 2. If you're in the 0.4 or the 0.8-ish range, 0.8 you can round up, okay? But if you're 0.79, you're not going to round up. You're going to multiply by 2.5. So we'll go back to these if needed, but it basically is a trial and error system to figure out what to multiply by. But these are just some common ones you'll see. All right, so let's actually do a problem, okay? And I'll come back to the rounding ones. All right, so this one is a special case. We have empirical formulas where I'm not giving you grams. I refuse to give you grams sometimes. Because we're so smart, we know how to work with percents. So if I ever give you percent of a certain element and another percent of another element, assume that you have a 100-gram sample. Then it's easy. You can get from grams to moles all day, every day. So if I want you to figure out the empirical formula of something, and I give it to you as percents, assume a 100-gram sample. Assuming a 100-gram sample for this one, how much oxygen do I have? 94.1 grams of oxygen, yeah? All right, now, how do I get from grams of oxygen to moles of oxygen? And this one, I think I've written these examples in your notes. Look for me. Your printed out notes is just 1 sheet of paper, 2 to a page. You guys can, just so you don't have to write down all the questions, you can write down the answers to the examples, not necessarily the questions. So it's like empirical formula question 1. All right, so you should also have your periodic table out. How do you get from grams of oxygen to moles of oxygen? Right, molar mass. So molar mass means your grams of oxygen has to go on bottom, your moles of oxygen has to go on top. I always write I1 with the mole, and then I have to write down the number of grams that correlate. So Giselle, what's the number of grams that correlate? This is molar mass. This molar mass is not something I make up. I don't get it from a problem. I get it from the periodic table. Josh. 16. I look at the periodic table and there's 16 grams associated with oxygen. So 1 mole of oxygen weighs 16 grams. This number in the front is going to change every single time. It's unpredictable. So I'm going to calculate 94.1 divided by 16. Calculator. So so grams and grams cancel. Tell me what you get for moles, Alex.
5.8812.
I'm going to stop at 5.88, okay? So I'm just going to truncate it. So this is how many moles of oxygen I just calculated, because that was step one. In the simple formula, take whatever you get it to moles. Bless you. We need to do the same thing for the other one. So how many grams of hydrogen am I starting off with? 5.9, because I'm assuming a 100 gram sample for my percents. So what's the molar mass of hydrogen? 1.008. Looking on the periodic table, right? So you said 1 mole of hydrogen goes on top because you want to get 2 moles. The grams of hydrogen go on bottom because you want to get rid of hydrogen grams. You look on the periodic table and you find that it's 1.008. So that one's really going to be really close to 5.9, but I think it's 5.85 if we're real stickler for the sig figs here, okay? So when you divide 5.9 by 1.008, your grams and grams cancel. You get 5.85 moles of hydrogen. All right, so how many steps have we completed on our little process of empirical formulas? Just one. We got it to moles, all right? Second step was to do what? Look back at your cheat sheet. You just wrote down your instructions. Divide by the smallest number of moles. Who's the smallest? 5.85, yeah? So I just write slash, which means divide by 5.85. Divide by 5.85. Okay, whatever you're dividing by, if it's the same one, obviously it's 1, right? So 5.85 divided by 5.85 is 1. 5.88 divided by 5.85 is still approximately 1. It's like 1.00. So it's still 1. It's really close. So what this is telling you the subscripts for the individual oxygen and hydrogen. It's literally saying I have 1 oxygen and 1 hydrogen. But those ones look silly, so we just write like this. So this is actually hydroxide. The empirical formula for what the information was given as, that's hydroxide, OH. So I didn't do any rounding, no funny business, because those integers were full integers. Yeah.
So when we write our answer, do we have to put the -1?
I normally actually will not give you polyatomic ions. I would normally give you something that's not an ion, but this one it was just for the first example. So no, you would usually never have a negative charge on there. All right, so same thing. Let's do this one a little bit faster because we know how our process works. What are you assuming when I give you percents? 100 gram sample. So tell me what I'm writing. You got this. Grams. Carbon. Okay, first step to do what? 1 mole of carbon over, right? You're looking at your periodic table and you say, oh, molar mass of carbon is 12.01. All right, so how many moles of carbon is that? Calculadora. 6.64 moles of carbon. Okay. All right, so we're halfway there. Oh. Okay. 20.2 grams of hydrogen. Next. 1 mole of hydrogen over, okay, because that's the molar mass of hydrogen. We're not making that up, right? We just look on the periodic table. So 20.2 divided by 1.008, calculadora. 20.04 moles of hydrogen. Okay, how many steps have we essentially completed? 1. Who wants to tell me the next step? Do what? Which one's the smallest? All right, so taking this number, which is smaller than 20, dividing both of them by the same one, because essentially you're just getting a ratio. So the first one, when you calculate, or you can just look at that one and go, that's definitely the single digit, that's 1. 20.04 divided by 6.64. 3.018. All right, is that roundable?
Yes.
Definitely, okay. So that's, oops, sorry, that's going to be a 3. So what I've just circled here are the subscripts, right? So I have a formula of C1, just not going to write the 1, H3. That is the empirical formula for our information given. We didn't have to round on that one either. All right, so let's get to a rounding one. Okay, so we just want to get a hang of the steps first. It gets very repetitive, but then you get really good at it because it's muscle memory if you keep doing these problems, okay? All right, so this one, 0.858 sample of an unknown substance is found to contain 0.321 grams of fluorine. The rest is copper. What is the empirical formula? Now, we're not giving percents here. We're straight up giving grams. So we are assuming a 100-gram sample? No, we got grams. Who wants to work harder? We are literally giving grams to start with. Let's go to moles straight from there. The only reason we do a 100-gram sample with the percents is because you can't really start with a percent. You have to start with grams to get the moles. So this one, you're going to start up with your two numbers. I'm sorry, this is grams. Your two sample information pieces here. How much copper do we have there? How are you doing that? You're just subtracting, right? You're taking your total sample. You're subtracting your grams of fluorine, so 0.321 grams of fluorine. So how much copper do you have? 0.537 grams of copper. Okay, so the two numbers that I've kind of squared off, those are your two numbers you're starting with in order to start the problem. We just had to do a little, business to get started here. All right, so I'm going to start off with you guys want to do copper first or fluorine? Copper, okay. So 0.537 grams of copper. All right? Next. Oh, I got grams. I don't even have the first step done. So how many grams are in 1 mole of copper? 1 mole of copper goes on top, right? 63.55 grams of copper. You just looked on the periodic table, you found the copper, you found 63.55. Okay? So this is going to get you moles of copper, which is, I got you. I'm going to write in scientific notation though. Don't be scared. 8.45 times 10 to the negative 3 moles, which is 0.00845. I just don't like leading zeros. It's just who I am, I'm sorry. Okay, so fluorine. So we got some moles of copper. Fluorine, you start with your 0.321 grams of fluorine. What's the molar mass of fluorine? 19 grams of fluorine. Okay, you just look on the periodic table for that. So 0.321 divided by 19 is, I hear you, 0.01689 moles of fluorine, okay? So I just wrote in scientific notation to get, a little diversity on the board here. All right, so what am I dividing by? Which is the smaller number? Actually, yeah, this one, because this one's 10 to the negative 3, this is 10 to the negative 2. So if you wrote this in decimal form, it'd be 0.008, blah, blah, blah. This one would be 0.016. So this is the smaller number up here. So I'm dividing by the smaller number. 8.45 times 10 to the negative 3. This number is dividing by the same thing. 8.45 times 10 to the negative 3. Top number is definitely 1. You're dividing by its own thing. Okay, bottom number is, I didn't do a rounding one. It's 2. No rounding needed. No multiplication needed. It's like 1.998. So I rounded that to 2. All right, so what's the empirical formula? CuF2. What's the name of that? Copper 2 fluoride. Good job. All right. This one, is this one? No, I'm not going to do this one. I think, are we feeling okay with this? You feeling okay? You feeling it? Let's do the molecular, which is just one further step from exactly what we just did. And it's this right here is the last step we have to do. So I'll let you write down this information. It's very little. And then we'll do 1 or 2 molecular formula ones so you guys have a good example to refer to. This is kind of what I was showing you earlier. Molecular formula is just literally a multiple of the empirical. So whatever you get for your empirical formula, you put it in parentheses, and you multiply by some integer on the outside as another subscript. That integer does not get, it has a method to the madness on how you get the integer. The integer is achieved by taking the mass of the molecular compound divided by the mass of the empirical formula compound. So mass of EF. That's how you get the n number, the integer that you're multiplying by. Bless you. So we're going to do essentially, if I give you a problem, if I start you off with percents, if I start you off with grams, you're going to do exactly the same step process you did to get to the empirical formula. But then after that, you're going to be given 1 or 2 pieces of extra information. Specifically, you're probably going to be given the mass of the molecular compound. You can find the mass of the empirical formula, because once you get the EF, all you got to do is add it up to get the mass of that. So you're going to get this last step, and then you'll figure out the molecular formula from that. So let's do an easy one, and then we'll do a hard one. So number 2, yeah.
So is this just adding on to like the empirical?
Mm-hmm. Yep. So if I say find the empirical formula, do what we just did. If I say find the molecular formula, do what we just did, and then this last step that we just talked about just now. Okay. So the empirical formula for C2H4, I'm sorry, the empirical formula is C2H4S with a molar mass. Molar mass of 179. This is what I just wrote down. This is a molecular mass. Sometimes we call it molar mass, sometimes we call it molecular mass, but that's the part of the formula we were just talking about. It's 179 grams per mole. What is the MF? What's the molecular formula? Okay. So the whole process that you just wrote down was N is equal to molar mass or molecular mass over EF mass. Yeah? So what's the molar mass of this one? 179 grams per mole. What is the EF mass? Or what would you need to do to get it? So 2 carbons is 2 times 12.01 plus 4 times 1.008 for the hydrogens right there, plus sulfur, 32.06. So this added together is going to be the EF mass, because the EF was given to us. The hard part was done, people. We didn't have to do anything. We just have to add it up. So that mass added up is, didn't write it down, okay, so 32.06 plus 2 times 4.01, 60.11 grams. All right, so 60.11 grams is our empirical formula mass, and that's just grams per mole as well. The units always cancel. No worries on that, okay? So 179 divided by 60. What approximately is that? What's 180 divided by 60? How much? 3, right, because 6 times 3 is 18. So 60 times 3 is 180, so it's just 1 extra 0. So you can do it in your calculator or in your head. That integer is 3. That makes our life easy, because all we got to do is take our empirical formula that we had, put a subscript of 3 on the outside, distribute that 3 in. Okay, so what's the new formula for the molecular formula? C6H12S3. There you go. That's the molecular formula. It's just a multiple of the empirical. That's it. You just got to figure out what the multiple is. All right. Next one, big dog. Here we go. So we've got a lot of information given here. So we're starting from scratch. We have to find the empirical formula for this one, and then we're going to find the molecular formula. So we got to get the baby workings first from step 1 through 3. All right, so we have a 0.400 gram sample of white powder that contains 0.14 grams of potassium. And I'm going to write down my givens as we go through reading this problem. So here's how I would start the problem. I would go, oh, okay, I've got 0.141 grams of potassium. And I've got 0.115 grams of sulfur. And the remainder being oxygen. So how much oxygen do I got? What are you doing in your head or on the calculator? What you doing? So add these and subtract from the original, right? Okay, so 0.4 minus the sum of this right here, which is That leaves us with oxygen being 0.144. If anybody else did that? Yeah? Yeah? Okay. Sorry, I actually have all my work right here. All right. So I just took my 4.4 gram sample, subtracted the potassium and the sulfur to give me the remaining oxygen left over. So this is 0.144 grams of oxygen. All right. Tell me next step, guys. Do molar mass, right? I'm getting to moles. I haven't even gotten to moles yet. So what's the molar mass of potassium? 1 mole of potassium weighs 39.1, is that what you said? 10 grams of potassium. All right, so I'll do the calculations for you if you guys just write down the example. You know me, love some scientific notation. 3.606 times 10 to the negative 3 moles. All right, so we've got 3.606 times 10 to the negative 3 moles of potassium. Next one, molar mass of sulfur. 1 mole of sulfur weighs, what do you say? 32.07 grams of sulfur. Okay, so if I take my grams of sulfur divided by my molar mass, mine was 0.06, so just forgive me, it might be a tiny bit off from what you calculate. 3.587 times 10 to the negative 3 moles. All right, then oxygen. Oxygen's molar mass. 1 mole of oxygen weighs 16. See, you accidentally memorize these things because you guys do it the same one so often, right? So 16 grams of oxygen. So 0.144 divided by 16 gives you 9.0 times 10 to the negative 3 moles. And you don't have to write this inside your scientific notation. You put 0.009 and so forth, okay? So, step 1 done. Got to moles of everything. Step 2 is? All right, so who's the lowest? Which one? First, second, or third? Second, thank you. Okay, so this one, because all of these are 10 to the negative third, so you just look at the front number to figure out who's the smallest. Second one's the smallest, so I'm dividing by 3.587 times 10 to the negative third. Dividing by 3.587 times 10 to the negative third. Dividing by 3.587 times 10 to the negative third. Whew, okay, I know it's chicken scratch, but there you go. All right, so this one in the middle is definitely 1, because you're taking it and dividing by the same thing. Top one, approximately 3.6 divided by 3.58, approximately 1, right? You can do some of these things in your head. So that is 1. The last one, 9 divided by 3.587. It's not 3, because that would have to be exactly 3 to get 3 there. So this is actually 2.5. It's not quite 3, it's 2.5. And we cannot put decimals as subscripts. So now, we have to do the whole rounding thing where we multiply. So this one's good, the 2.5 is not good. So what we need to do is, whenever we multiply this one by, to get to a whole integer, we do it to the whole shebang. No special treatment, you do it to everything. So what am I multiplying this one by to get to a full integer? 2, right? Question? If any of these numbers came out to be like something 0.2, you would round down to the lower number. If it was like something 0.8, round to the upper number. But if it's anywhere in between, you have to multiply by something. And I'll go back to my rounding rules in a second, because I'm like 4 slides ago. I'll show you. But if it's 0.5, it's easy. You multiply everything by 2, and then you'll get to a full integer. So multiply this one by 2. 2.5 times 2 is 5. So the new subscript for this one is 5. But if I do that to 1, I have to do it to all. So that one times 2, and that one times 2. Sorry, I'm running out of space. So I have how many potassiums in my empirical formula? 2. Because like I just said, 1 times 2. So there's 2 potassiums in my empirical formula. How many sulfurs? 2, because I multiplied that 1 by 2. How many oxygens? 5. That does not look like something you're familiar with. That's okay. We're going to see some crazy empirical formulas, and that's okay. So this is the EF. We just took the grams, we went to moles, we took the moles divided by the lowest one, we got 2 subscripts, then we're like, oh no, we can't have a 0.5 subscript, multiply everything till you get to a whole number. That's the empirical formula. Now, the rest of the problem says, the experimental molar mass is 859 grams per mole. What is the molecular formula? So, how do you guys want to accomplish from this to get to the molecular formula? take the what mass? Okay, so I need to get this mass too. Okay, so N, I need to find N essentially for my multiplier across the board. I need to get the molecular formula mass. So molecular formula mass is given to me above as 859 grams per mole. 859 grams per mole. Okay? I need to divide that by the EF mass. And that I have to calculate. So I need to add up 2 Ks plus 2 sulfurs plus 5 oxygens. I know you're doing that in your head right now. Tell me if this is what you got in your head. 222.32 about grams per mole. All right, so this is the EF mass. This goes in the denominator. 222.34 grams per mole. Good. Huh?
You switched.
This is what.
Two up there.
No, my bad. My bad. Okay. Thank you. Okay, so 859 divided by 222 is about 4. It's actually 3.86 if you do it in your calculator. 3.86 rounds up to 4. Okay, so the integer that we're multiplying by is 4. So what is this purpose of the 4? Essentially, we're taking the empirical formula, we're multiplying by 4, all those subscripts by 4. So what's the molecular formula? K8, S8, O20. Whew. Molecular formulas are going to be bigger and better. All right, 8 o'clock. Sorry, I have to do quite a few examples. I try to go slower today so you guys have time to write down every single step possible. You guys have some practice questions, and I'm going to minimize some of those, okay? So I think you guys will get it if you get it. So if you can do 2 problems and get it versus 20 problems to get it, let's go with 2. So on your problem, you have these problems in front of you, yes? On your paper? Find your printed paper that I gave you. I'm going to circle some of these, and those are the ones I want you to practice right now and ask me questions, because you will see them on your problem set tonight, and I'm not here for tutoring after school today, so I'll make sure you're taken care of. So, my favorites are, let's see here, 2, 4, start with 2 and 4 on the top practice, and I'll circle some on the bottom. Work with a partner, get your calculator out. I'll turn on some music in just a second. I'm gonna start with these 4, okay? So I got 2 and 4 in the first practice, and 1 and 4 in the second one. I'm gonna see how we do with those, and if I need to, I've got 1 more in mind. So I was gonna do half of the problems, because there's 10 up here. I was gonna do 5, but I got 4 up there. So you guys practice that, and then I'll see if we get to one of our games today. So let's go 20, maybe 20 minutes practice max. Okay, I'm going for like 15 really. Yeah. Yeah. You have your sheet in front of you? You didn't get one from the first day?
Do 4 and 1, that's it.
Raise your hand if you don't have this sheet. For some reason.
Not if we're just being wacky.
The purple one is probably your best bet.
Purple one's kidding.
Yeah? I'm coming. Let me just stop this recording. Oh, please tell me I actually recorded today. Yep, forgot.